So in this video, we're going to explain a couple pre-lecture problems from class on 827, the solutions we discussed in class. The objectives of these videos are to apply the addition rule to compute probabilities, and also to use set notation to represent unions and intersections of events. And both of these are also objectives from the Exam P actuary exam. So the first question stated here, for a bill to come before the president, it must be passed by both the House and the Senate. And we're given several bits of information. We're given that 60% of all bills pass the House, and that 80% of all bills pass the Senate, and 90% pass at least one of the two. And our goal is to calculate the probability that the next bill presented to the two groups will come before the president, meaning it will pass both groups. So we have sort of two events of interest here. The first event, which we're just going to denote by capital H, is the event that the next bill passes the House. And the second event, S, is similarly that it passes the Senate. And then we're going to discuss the solution to this problem in two ways. One, by sort of intuitively drawing a Venn diagram and working out the solution geometrically from that. And another by sort of using more formally the addition rule and using set notation to represent events. It's useful to do this problem in both ways. So first, to draw a Venn diagram of the situation, let's suppose this is our universe of all bills. Here are all the bills which pass the House, and here are all the bills which pass the Senate. And the fact that 90% of all bills pass at least one means that if I sort of highlight this combined area of the two circles here, that whole combined area is going to be 0.9. Which means the outer area would be 0.1, so 10% of all bills don't pass either House. Now, to reason out, now what we're really after here is this intersection, right? The bills that pass both. And to reason out what this should be, I think the easiest way is just to note that 80% pass the Senate, which means that this S circle right here should be, excuse the poor tablet usage there, should be 80%. And so if this whole combined, two circles should be 90% and the Senate circle should be 80%, then you can reason out that what remains here in the House, there's 10% which pass the House but not the Senate. And since we have a combined 60% which pass the House, that means that this area of interest here would be 0.5. And that then in turn is at least the fraction of bills which pass both. So we could say that 50% pass both. Now for a more algebraic solution to this problem, what we could do is write out the given information, say that P of H is 0.6, P of S is 0.8, and the area represented by passing at least one of the two is given by the set theoretic operation of unions. The probability of H union S would be 0.9 here. Now we know from the addition rule that probability of H union S is the probability of H plus the probability of S, but then minus the probability of H intersect S. So this last bit here is the bills that are in this cross-sectional area between the two, right? So if we add together these two circles, we double count this middle intersection, and that's why we subtract it back out if we really want the union. So now we just look at the information we're given. We know that this one is 0.9. We know that these are 0.6 and 0.8. And this one is our unknown. We'll just relabel it x. And now we just have a simple algebraic equation which we can solve for x to get x equals 0.5 as before. The second problem from these pre-lecture notes is slightly more complicated in that it involves a Venn diagram of an intersection of three separate events. So we're going to talk about how to use the principles of Venn diagrams to kind of figure out a problem like this, and also how to represent the events of interest as a set theoretic operation. So here, your friend convinces you to take part in the speed dating event for engineering and science majors, and you're given a bunch of information here. So in a problem like this, I think the first step is sort of to look at your information, identify what the events of interest are, and create an appropriate Venn diagram, which kind of helps you visualize and break up the information into smaller pieces. So here, it's clear from kind of the first given statement here, right, that there are males, and second, and obviously there's going to be females, as you can see in the second statement. There's ECS majors, and we also know that sort of complement of that then for our universe is going to be science majors. And it looks like there's also going to be information about students with brown hair, so we could take the complement of that to be students who don't have brown hair. So I'm going to first of all define three events. M is the event that the student selected is a male. E is the event that they're ECS major. And then B is going to be the event brown hair. So now I'm going to draw our universe up here, overlapping with the problem, and I'm going to draw three circles for male students, engineering students, and students with brown hair. Now, the first bit of information, 5 male ECS majors have brown hair. That means that this little circle in the intersection of all three, or this little wedge in the intersection of all three is going to be 5. The second bit of information says, so we've kind of taken care of that condition here, right? Now, the second bit of information here says that 10 female science majors have brown hair. So that means if I look at this brown-haired chunk, I want to look outside the engineering, and I want to look outside the male. So that sort of means this wedge right here gets filled in with 10 students. The next bit of information, so now I've taken care of this, 10 male students with brown hair. Well, that means that this sort of ellipse in the intersection of male and brown hair, the total here should be 10. Since I already have 5 in this inner part, that leaves 5 in this outer part, in the intersection of male brown hair science majors. So we've taken care of the third condition. Now 15 ECS majors have brown hair. That means that this ellipse in the intersection of brown and engineering should total 15, making the engineering brown-haired females, this little segment here, 10. 12 male ECS majors. So that means this wedge between males and engineers should be 12, leaving 7 for this chunk here. So that was, let's see, where are we at? We took care of 12 male ECS majors. Now we have 30 ECS majors. That means this whole circle here should give us 30. And let's see, we've taken care of 22. That leaves us with 8. And we have 25 males remaining. We've taken care of 17 here. That leaves us with 8. And finally, we know that there's 30 science majors. So that means everything outside of this engineering bubble here should be 30. And it looks like if we count up what we've got so far, we've got 18, 23. That leaves us with 7 students in the outer universe here. So, all right, so now we've sort of taken this problem and filled in each chunk. And each of these chunks, remember, involves an intersection of 3 events. For example, this outer chunk here, right, of 7 students. If we wanted to classify those students, we would say they don't have brown hair, so they're in brown complement. They're also not engineering majors, so they're in E complement. And they're also not males, right? Or in words, we could say that they're, not brown hair. And the complement of engineering here would be science, and the complement of male here would be female. And if we look down at what the question is asking us, what's the probability that you're paired with a female science major who does not have brown hair? Well, that's exactly the event we want here. EC intersect MC. And we know that there are 7 students in that bubble. And so to figure out the probability of getting paired with one of those students, we would just divide by the total number of students in the space, which you can easily tally up to be 60. And that gives us the desired probability. Now, you might have also interpreted this as saying, I guess a little bit of this is how you interpret, who you're paired with. For example, if you're a male, are you only going to be paired with female students, or is this sort of, you could get paired with a male student as well? So if you think, you should only get paired with female students and you're male, then you might want to change this denominator to just be all female students, in which case you would add up all the entries outside the male bubble, so 17, 27, 25, and that would be your new denominator here. Now, a problem like this, you can also use addition rule for 3 events here, but that gets messy in algebra, and the Venn diagram way of solving these types of problems is sort of a much simpler visualization.